thanks very much to the organizers and to all the other speakers and poster presenters. I've learned a ton at this meeting and had a lot of fun. I'm in the convective section, and I'm a good transition because really I'm going to talk about a bunch of stuff Craig talked about. And Craig and I are aiming at the same things, but Craig has gone very parametric. So we had gammas and inverse gammas. And I'm trying to get entirely away from distributions at all. And I'm this close. Okay, there's a little bit of Gaussian tails still. But Craig also talked about the way that I think about ensemble data assimilation as this sort of two-step bivariate problem. I'll just show it in pictures. This slide was made in 2002, so apologies to people like Eugenia who've seen this slide dozens of times. But the basic idea of the way we think about ensemble filtering is that there's some ensemble, so 3 members here. Standard thing, you make a forecast to the time at which you have observations. You apply the forward operators to each one of the ensemble members, 3 here. And the way we think about it now is we do this one observation at a time, sequentially. So we have a scalar problem, 3 values of the observation. The instrument gives us a value. The instrument designers give us some error distribution. Then we're going to do some one-dimensional filtering problem. We'll talk a lot about one-dimensional filtering problems in the rest of this talk. That one-dimensional filtering problem gives new ensemble members in blue and increments from the old ensemble members. So this is what Craig was doing in all his observation space stuff. He was using gammas and other things to get these increments. I'll talk about later, we can compute the increments without almost any distribution assumptions, certainly without Gaussian assumptions, and Craig showed you that. And then as Craig went on to do too, then you can update all the state variables by just using linear regression with the bivariate ensemble prior between the observation and each state variable. And those are independent computations, so that's where we get our parallelism, but it's also where we get our simplicity. All you have to think about in the worst case is a bivariate problem. And so I don't write down matrices anymore at all. I've actually kind of forgotten how to do it. And then when you're done with all the observations at this time, then you move on, and it's all the same thing. So what I want to talk about quickly to start with is the observation space update here. This is old. This is work from 2008, but not that many people have seen it. So this is the rank histogram filter. So in this cartoon, I have 5 prior ensemble members from about -1.5 to 2.5. And I'm just going to make the following assumption. This is consistent with the ideas that a rank histogram is used to evaluate ensemble distributions. I'm going to assume that 1 over n plus 1 of the error of the probability density is in each one of these things. So these 5 guys divide the real line into 6 partitions, and I'm just going to put 1 over 6 of the probability mass in each one. And in the interior ones, I'm just doing it completely naively, just uniform between these things. And so if 2 are closer together, the probability is higher. If they're further apart, it's lower. Then I have to worry about the tails. I want 1/6 of the probability in the tails too. And this is the one parametric part that's left here. So there's a way to fit a Gaussian tail to these things so that those Gaussian tails also have 1/6 of the mass. And the details of that are trivial, but I don't want to do it in a short presentation. So this is my prior. I'm just going to do Bayes now. So I need a likelihood to go with that prior. And traditionally, we've done this with Gaussian likelihood. So here is a Gaussian likelihood, and I've highlighted the value of the likelihood at each one of the ensemble members. I want to do a product now of these, the prior in green and the likelihood in red. And sorry, Craig and I mixed our colors up here. We should have coordinated if I'd realized exactly what it's going to do. To make things a little bit simpler, I'm going to go to a quadrature approximation. So I'll assume that the density inside, the likelihood inside this has this linear form. Okay, I'll keep the Gaussians on the tails. And so then I'm just, in each one of these things, I'm just taking the product of the red and the green. So the products are the blue. There we go. So these are just trapezoids. And in the tails, I actually have a product of a Gaussian and a Gaussian, part of a Gaussian and part of a Gaussian. Well, that's just the standard, in this case, EAKF, whatever your favorite way to take products of Gaussian is. So this is the posterior in blue for the rank histogram filter. And now the trick is I've got to come back up with an ensemble. And that's the motivation for this kind of weird, obtuse way of doing this stuff. So in my posterior, which I'm showing in blue here, I'm simply going to pick 5 members so that they partition the posterior probability distribution into equal things. So 1/6 of the posterior is outside, 1/6 of the posterior is between each pair of these. And this gives me this ensemble here. If I compare this one, so this is sort of relatively Gaussian. This is what you would get from a deterministic EAKF type update. But if you go to other types of distributions, the behavior is quite different in observation space. So here's an example where the prior has one outlier way over here. The rest of the ensemble's here. The rank histogram knows to, and the observation likelihood is broad and over here. The rank histogram knows to eliminate this stuff. The EAKF leaves this thing hanging out here. And an ENKF would do the same thing. It would just be jittered around a little bit. For bimodal distribution, so here's 3 ensemble members here, 3 ensemble members here in the prior. The RHF pulls things in. The square root type filters, the ENKF, leave this sort of embarrassing blob out here where there's not really much likelihood. So in one dimension, actually, this thing is a nice, generic, nearly non-parametric way to do things, and we found it to be extremely effective, so we often use this instead of the EAKF for many of our large applications in observation space. And this is relevant, of course, for some convective type problems. But now I want to do a thought experiment. If I go quickly back here. So I had a likelihood that was normal in the space of my observed variable, but so what? I don't need that. So let's suppose now that this is actually the prior for some state variable. It's not the observed variable. I have some other observed variable. Well, I can compute the likelihood at each one of the probabilities. This is what I'd do in a particle filter, basically. Okay, so there's a likelihood. It doesn't look nice and Gaussian or continuous anymore. And in fact, the beauty here also is that it doesn't have to be nice and Gaussian and continuous for the observed variable either. It could be some bounded quantity. It could be a logarithm taken. It could be bimodal, whatever. All I have to be able to do is compute the value of the likelihood at each one of the priors. And then I can do the same old algorithm, okay, with one exception. Inside, I can fit the likelihood just with a series of linears. The one trick is out on the tail, I have to do something. And so what I actually do on the tail is I assume that there is a uniform. And this is related to Craig's, the thing that generated discussion. There is a uniform out here. That uniform is made proportional. It's really infinitesimal and uniform if you look at the things. But it's made so that the product of this will give the appropriate weighted amount of density outside this likelihood. Okay, so this is the only difference from the standard description of the rank histogram filter as these tails. Okay, I can do the same thing. Products of my prior and my likelihood. Green times red gives me blue. 2 Gaussian tails again. 4 linear interiors. And then I can do exactly the same thing. I can find posterior members so that 1/6 of the density of the blue is in each one of these bins. And again, a comparison to an EAKF here. In this case, the EAKF sort of slaps stuff into this middle place where maybe there's not so much likelihood. So I've updated the marginal distribution for a state variable, any state variable. I can do them all in parallel again. And there's a whole bunch of theory missing here, all you smart people. Okay, so there's at least a dozen people who have corrected my work before in this audience. So the rest of you can join in with that crowd. I don't have all the theory behind all of this. But now I'm going to say that I can update the marginals of every single state variable whenever I want. Okay, so now I'm going to throw out an entirely different way to do filtering. There's my forecast, same as before. Compute my forward operator, same as before. Okay? Get the stuff from the observing system, same as before. But now, I'm not going to do, I actually don't have to do any computation in observation space except computing the likelihoods. Okay? So all I have to do is compute the likelihoods, and then I can just use this RHF algorithm to update every one of the state variables. Great. So I knew this in 2008. It's in the conclusions of the rank histogram filter paper there. And because I was stupid for a decade, it says that you should be able to do this, and I can never get it to work. And the trick, of course, is that I'm getting the marginals for all the state variables, but I'm not getting any information anymore from a regression that says how to pair those marginals up in an ensemble. Okay, so if I know that there's a value of 6 for one state variable, do I put that with value 4, value 11, or value 27 from another state variable? And so the trick in this particular case is I'm just pairing the smallest value in the updated state ensemble goes to the same ensemble member that had the smallest one before. Okay? So in essence, I'm just nudging these things around. Oh, I hate that nudging word. But that is what it is. Okay? Do the next observation. Then you're done. Okay, so I'm going to show some bivariate priors now, many of them motivated by things Craig had, many of them motivated by different other things. So one example is, many people have looked at this, but there's some really nice work by some of our hosts, Kondo and Miyoshi, in nonlinear processes. think, I don't know if that's accepted or not yet, but it's well along in the process. And they point out from these massive ensembles that they have here that you can see all kinds of interesting bimodal type behavior and outlier behavior in convective regions, especially in the tropics. So many of you who've used Dart will have seen these plots, and you will be able to get more out of them than I can explain to everyone else. For people who haven't seen them before, just look at this central plot, basically. And because Craig's from Australia, our plots are rotated versus each other. So I actually have the unobserved state variable over here and the observation here. Craig had it the other way. Doesn't matter. So this is an example where the priors, shown in green, are bimodal. Okay? And the observation is here for the observed variable. The observation is the red thing there around 7. Okay? And there's details of the observation error distribution over here again for those of you who know. So if I do a standard EAKF, I get a posterior that looks like this blue. Okay, again, it embarrassingly drags stuff. Everything has to move along the linear regression line, and it leaves this thing in the middle. Okay? This is what happens if you do an RHF just in observation space. So this still involves regression, so you can see the straight lines showing how you move from the priors to the posteriors. But it did use the rank histogram filter, which eliminates these things out. And so in general, most of the mass moves into the place where you would like it in the mode that is observed. And in this case, the state RHF, so this is the new algorithm I'm talking about, does more or less the same thing as the RHF, although you can see the first hints of the power here in that these lines are no longer parallel along the regression line. Okay, so the increments no longer have to all be along that slope. There's no regression going on. So let's go to another case. This is one with an outlier. So the prior is the blue band here, and this outlier here. The observation is inconsistent with the outlier, and an EAKF does this now. So again, you can see all the increments are parallel to the regression line, but it leaves the outlier hanging out in no man's land. This is an observation space RHF, so been available for 10 years. Okay, maybe a little better, maybe not. And this is the algorithm I'm talking about now. So probably better. And again, you can see definitely not along the regression slope. Okay. So there's a bunch of other distributions which one can motivate with advection and other things. This is the tie-in to the mesoscale part, but I don't want to focus on that right now. These are distributions that one might get. So here's an example. This is like one of Craig's. This is a measurement where the, well, it looks like an x squared, but this is actually a cosine trace rate advection. But the prior is the green here. Okay? And the observation is here. An EAKF pulls stuff along the regression line, so everything moves off the prior. The RHF has the same problem. Everything gets pulled off the prior. Here's the prior for the new algorithm. Okay, you can see things move in a different direction. It's not clean. Okay, so this isn't a particle filter with like a billion particles, but it's a lot cleaner than the others. So you get a nice bivariate distribution generated from a continuous prior. This is another example. This is the square forward operator, just half of the lobe that you had, Craig. It would work the same with the full lobe. So the green's the prior. Here's what an EAKF does. So it squishes this thing off the slope. Here's what the RHF does. Here's what this new algorithm does. So you get everything moving up along the line more or less. There's still noise, but consistent with this. Let's skip that one. So these are just other examples of this. So again, there's lots of problems here. This is not a panacea for every prior you can think of. And this is an example of where things get ugly. So this is a prior which you could actually get if you have uncertain advection of a front, and that front is moving a significant part of its length scale between observations. You can end up with part of your domain where you have this and the other part down here. And so this is a distinctly bimodal prior. The EAKF does this, again, along the regression line, which really has nothing to do with the prior anymore. The RHF does this, not much better. And here's what the new algorithm does. Okay, what the heck is this thing doing? I mean, it's doing what it's doing. It's not clear that this is any better. It might even be worse. Okay, so this doesn't fix everything, but it fixes a lot of things that are not accessible stuff. And there's no parametric assumptions necessary right now. I don't have to say this is a case for a gig or this is a case for a EAKF or whatever else. Okay. So quickly, I'm going to show some tests in Lorenz 96, 40 state variables. We've all seen it. I'm going to mix up the forward operators, and because of time, I'll just look at 3. So I have 40 randomly located stations around the circle. I might do identity observations, square root observations, where I take the signed square root of there, or square observations. I'm going to compare the traditional state space algorithms, EAKF, the NKF and rank histogram filter, sorry, observation space. So these have been around forever with the new one. I'm comprehensively tuning the inflation and localization for each one. An interesting side I won't get to is with some of these forward operators, you actually need to deflate to get the best performance, which I'd lost track of over the years. So anyway, I'll tune these things up and compare them. And the plots I'll show to compare them are going to look something like this. I will do a number of different cases trying to span from very, very confident and linear to very, very unconfident and nonlinear to cases where the observations are much more compelling than the prior and cases where they're much less compelling. And the plots will look like this. There'll be pairs of bars. The assimilation period here, so I looked at 5 different really rapid to less rapid assimilation. And the left-hand column is going to be from the best observation space method, the right-hand column from the new thing. And then on a slide, I said 5 assimilation periods, I will have 4 panels where the observation error variance increases from very small here, 1, 2, 4, 16. So I'm just trying to span some selection of frequency of assimilation and observation error variance. When you have very frequent and very good observations, well, Gaussian and linear is pretty good, and it's hard to beat. And that's a theme, I think, of all of us who are trying to work on these things. If you use your algorithm that doesn't assume Gaussianity and linearity, you can't beat Gaussian and linear when things are almost Gaussian and linear. As you get to more and more observation error, the new algorithm is generally better, and it's better for the ones that are less frequently assimilated that have higher RMSE. And this is a summary plot of that particular case, which was for identity observations and 80 ensemble members. Here we're seeing the ratio of the new algorithm to the old algorithm. It's better if you're below the 1 line here. As the assimilation period gets longer, and within each assimilation period, as the observation error gets larger, then the new algorithm tends to be more competitive. I'm not showing statistical significance here. I did run multiple cases. Basically, every difference except 2 of them in the entire thing is significant with paired t-tests at 10 to the minus 10th on these things. So differences mean probably something. Okay, so this is kind of mixed. So for larger error, this does better. It's not as good when things are really linear and Gaussian and identity observations. So now I'm going to do square observations. This is Craig's example case. And so now I actually only did 3 different error variances in this case, still the same 5 assimilation periods. The color is actually saying which state space method did better, and I'm confused about this one, so I'm not going to talk about it in a limited time. But the comparison now is, again, the black columns are the new method in comparison. This is a really hard assimilation problem if you haven't tried this with standard filters. We've had a group that's been working on this for years, and it is just makes your head spin with this square thing. So there's lots of trouble with the standard algorithms for small observation error variances. But this is the summary plot. So again, if you're below the 1 line, the new algorithm is doing better. Obviously now it should have some advantages because this is not linear and Gaussian, and in particular it does much better for this extremely difficult no man's land in the middle. So almost universally better in this case. This is a case for square root observations, so the other concavity from what Craig was looking at. Again, going to bigger and bigger error variance, longer and longer assimilation times. And again, the summary looks like this. In this case, again, you expect it to do well, and except for a few cases with small error variance, the new method is not only better, but it's significantly better. I mean, these are big differences for these types of things. I'll skip over the 40 results. It does work with 40, but it's more interesting to look at large. So this is for the identity observations now with 160 ensemble members. Okay, and the summary plot says that it is becoming more and more competitive for smaller errors here. So with a larger ensemble, you're able to resolve more subtle nonlinear, non-Gaussian behavior. And again, if you go to the square root observations with 160 members, now it's almost universally better and significantly better. A final case I want to show, and we saw some results like this from Ibrahim yesterday. So if you compare 160 members with the standard observation space to 80 members with the new space, for identity observations, For identity observations, it's not better in general. But if you go to square root observations, even with half the ensemble size, it's better in almost all the cases. Okay, and so in Ibrahim's case, you were weighing off cost. So what is the cost here? So it turns out we have to worry about the impact of p observations on m state variables. And so in the standard method, you have to do the regression. So the cost is m, the number of state variables, times the number of observations, times the ensemble size. Okay, if you do a naive implementation of the rank histogram filter, you get this extra log n term, which is from having to do sorting. But that's not an exponential there, by the way. But if you do a clever sorting, because these things are almost sorted to start with, you can actually get the cost down to the same scaling. Okay, so quickly then, there's an even more interesting way, and this is what was used in these results. So just like with a particle filter, you can multiply the likelihoods together for each particle. You can do that here too. So I can do my multiplication of the red likelihood for each ensemble member just up front, and then just do the rank histogram filter once at the end. Okay, and suddenly that brings this cost down to O of mn plus O of pn. Okay, so it's actually faster. And in fact, in this case, the actual timing was significantly faster for the new method than for the old method with the same ensemble size. Okay, so conclusions. This is a filter without regression. For the problems I've shown you, it can be competitive with standard ensemble filters for larger error variances when things aren't too linear and Gaussian. It is about the same cost. There are all kinds of interesting ways to parallelize this computation that are not available in standard methods, which are pretty interesting for exploiting different types of communication patterns and things. These methods, of course, are interesting, and they're in this mesoscale session, and Craig was getting there because high resolution and high frequency problems tend to become more nonlinear and non-Gaussian. You can't solve that type of problem by just increasing the ensemble size, so you got to look for something else to do, and we've seen many, many methods here. This is just one. There was a mention yesterday, I now can't remember who asked the question. So Matreff and Snyder and all tried to extend the RHF in 2014. They took a slightly different approach, and it doesn't scale. The computational cost doesn't scale, but there's some relationships here. And then this is a more generic question here at the end. I've worked now with 5 different people, including Craig, who've come in to put their nonlinear algorithms in Dart. And the question always comes up as, well, this works okay, but in cases that aren't that nonlinear and non-Gaussian, not so good. So if I could only apply it in the times that I needed it, but not the other times, that would be great. But everything's noisy. I can't tell what's what. And so this question of how to identify when it's good to use better algorithms, I think is generic and really important still. So this is all available in Dart. Craig's method is in Dart. Dan Hodis's method is in Dart, and other things if people want to compare this. And thanks for your attention.
Thank you.